method of images. So this is basically used to find out the electric potential, field, right, and flux density and all for this kind of configuration. Say this is a conducting plane, an infinite conducting plane, okay, it should be infinite and it should be grounded, and here you have a charge. So in this case, if you want to find out, this is a charge Q, so if you want to find out some electric field or potential, say at some other point, say x, y, z, P at x, y, z, okay, then how do you do this? How do you find the electric field or the potential at point P? Okay, so for that we are going to use the method of images. So what does it say? It just says that whenever there is a charge and a conducting plane like this, you just have to replace this with an equipotential surface. So in place of the conducting plane, you have an equipotential surface, okay, and here there is a charge plus Q. Let's say the distance is some h, okay. So on the opposite side, at the same distance h, you are going to have another charge minus Q of equal magnitude but opposite sign, okay. So now there is an equipotential surface here and there is a charge plus Q is as it is, no change, but you keep a charge, a negative charge or a charge that is opposite in sign but of same magnitude at the other side of the equipotential surface, okay, and then you just have to find out the, so if there is the same point P, right, so you can find out the electric field or potential due to just these two charges. So this isn't just applicable to a point charge, here we took a point charge, but this is applicable to any charge configuration. So for example, if there is a conducting plane like this and let us say there is a line charge, okay, uniform charge density rho L, let us say, okay, then what is going to happen? On the other side, you just have to replace it with its image. So this is as it is, rho L, okay, so just the image, right, at equal distance. Let us say this is H1, so at H1 it is going to start and this is at H2, right, this is H2. So here also at distance H2 the other end will be there, so the line charge is going to be like this. What will be the charge density here? This is going to be minus rho L. Similarly, if you have a volume charge, okay, so let us say rho V coulomb per meter cube, let us say, okay, so then what it will be replaced with? You will have a spherical charge here at the same distance and here its image. What is the charge density here? It is just the opposite, minus rho V. So if this distance here is h from the center, if you are taking, this distance will also be h, okay. So that is how you have to replace any charge that is present along with the conducting plane. You can remove the conducting plane and you can keep its image, okay, image with respect to the conducting plane, okay. Remember, the conducting plane should be infinite and it should be grounded, okay. So what will be the equipotential surface potential? The potential is same everywhere on the equipotential surface, but what is the potential? It should be 0 because the conducting plane is grounded. So you can write the statement for this. The image theory states that a given charge configuration above an infinite grounded perfect conducting plane may be replaced by the charge configuration itself, its image and an equipotential surface in the place of the conducting plane. Okay, so we will do an example, then it will become more clear to you. Here the question is, a point charge Q plus Q is located between two semi-infinite conducting planes intersecting at right angles as shown. Okay, so here you have one conducting plane, here you have one conducting plane, but they are only semi-infinite. That means in this side it is not infinite for this plane, right? And for this horizontal plane, vertical plane, on the other side there is no plane. Okay, so it is semi-infinite. So find the potential in the region x is greater than or equal to 0 and y is greater than or equal to 0. That means in this region, right? This is the x axis, this is the y axis. So we will draw the image, right? What will be the equivalent image diagram? Okay, so we will just redraw this conducting planes. Here there will be plus q and this distance is given as a, and here the distance is b. Okay, and this is grounded. Now instead of these conducting planes, we are going to replace them by equipotential surfaces. Okay, so this is an equipotential surface, and what will be the voltage? It is going to be 0. Why? Because it is grounded. So now simply the first two images you can draw. When there is Q here, there is an image with respect to this plane here, and with respect to this plane it is going to be here. Okay, so first we will draw that. At distance a there is a charge. What will be the magnitude? Magnitude is q, but the sign is going to be opposite, minus q. Okay, and here at a distance b there is a charge which is minus q again. Okay, but once again you have to draw the images to these charges as well. Okay, only then it is possible to have an equipotential surface here. If you take any point on any of these equipotential surface, what should happen? The force should be same everywhere, then only the potential is 0, equipotential, right? So this means that you have to extend these conducting planes and draw the images about that particular planes as well. Okay, so this will be, what will be this distance? It will be b, right? And this distance is also, it should be b, and this distance is a. Okay, so that is how you have a charge here. And what will be the magnitude of this charge? It is going to be, magnitude is going to be same, no change. Okay, but what about the sign? Now this charge is a image of this and this charge. Okay, so these both are negative. So what should be this charge? It should be positive charge. So it is plus q. Now once you have drawn this configuration, then you can very easily find out the potential. So we want the potential at any point x, y, right, in the region x greater than y greater than 0. So this is pxy. So in order to find this, you have to note down these coordinates as well, then only it will become easy. This is a comma b, right? And if you take this charge, this is having the same y coordinate, okay, but the negative x coordinate. So this is going to be minus a comma b. Similarly, this point you can get minus a comma minus b, and this point is a comma minus b. Now you can find out the potential at P. So first we will find due to this charge. Okay, so what will that be? The charge is plus q divided by 4 pi epsilon naught r. So what is r here? It is the distance between these coordinates we have. So you can directly write root over x minus a whole square plus y minus b whole square. So this is due to the first charge, the original charge. Okay. Then if you take due to this minus q at minus a comma b, then what will be the potential here? This is going to be minus q, because the charge is minus q, divided by 4 pi epsilon naught. And what will be the distance here? From the coordinates you can find out x minus of minus a, so x plus a whole square plus y minus b whole square. Okay. So this is due to minus q, this charge. Next you can find due to this plus q. So this will be plus q divided by 4 pi epsilon naught root over x plus a whole square plus y plus b whole square. And finally, due to this charge at a comma minus b, the potential is going to be minus q divided by 4 pi epsilon naught root over x minus a whole square plus y plus b whole square. Okay. So if you add all these terms, then you are going to get the potential. Okay, potential at P, that is x comma y.